I'm delighted to be joined by a panel of three excellent experts and speakers today, who are going to be discussing nuclear security for small modular novel advanced reactors. Bit of a mouthful. We have Dr. Ross Peel from King's College London. We have Dr. Chris Hogarth from the Department of Nuclear Safety and Security at the IAEA. We have Dr. Anita Nielsen, who is an independent consultant. So thank you all for joining us today. And what I will do is perhaps hand us over to our first speaker. So Ross, over to you.
Thank you very much, Carl. So good morning, everyone. Good afternoon, good evening, wherever you may be in the world. My name is Ross Peel, and I'm going to kind of speak briefly to this topic to introduce some of the concepts behind it. And this is based on work I've recently done with my two co-authors, George Foster and Sukesh Agara, who are named on the slide there. Could we have the next slide, please? So for those who are not necessarily following these developments, we're now in a stage of nuclear power development where we're moving away from large conventional nuclear power plants to a certain extent into what we're now terming evolutionary and innovative designs, EID. And this is kind of a terminology that's developed quite a lot in the last few years. We once talked about small modular reactors, SMR, advanced modular reactors, AMR, and those terms are still used, but they're now collected under this umbrella term of evolutionary and innovative reactor designs. And effectively what we're talking about is, in terms of small modular reactors, which is one half of this, are evolutionary designs based on technologies that we have in the world today or are kind of undergoing deployment now, but versions which are under 300 megawatts in size, electrical usually, and that are the modular part comes from their ability to be made in factories, rolled off a production line, transported to a site, and then installed in a very different way than we see on-site large-scale construction of large power plants. The advanced reactor side of it usually comes from generation 4 technologies, so revolutionary designs as opposed to evolutionary designs, according to the kind of 6 reactor types described by the Gen 4 International Forum. So various fast reactors, molten salts, supercritical water reactors, and very high temperature reactors. And my colleagues, well, my fellow speakers rather, will speak about some of these in a little bit more detail coming up, where I will kind of try and skim over the general things about all these different reactors in one go. So across these this suite of EID designs, and there are about 100 of these, there are a range of differences, but we've kind of tried to collate these differences against large conventional nuclear power plants into 6 categories. And what I'll do momentarily is go through each of these in a little bit more detail. But the key message that I want to give really is that each of these sets of differences creates a set of security and or safeguards considerations. And it's vital that all stakeholders in the nuclear sector, and particularly when it comes to EID, are really kind of playing their part in addressing these and working collectively. And we need to kind of start addressing these now in order to bring the benefits of maximizing security and safeguardability at the lowest cost to both developers and operators, national governments, and indeed the international body, the IAEA. So could we go to the next slide, please? So all of these differences that I'm about to go through are collected in a report, and I'll provide a link to that report at the end of my talk. But to kind of run through them very quickly and briefly because of the time we have available. The first set of differences concerns power capacity and modular manufacturing construction. So being smaller, being modular in nature, meaning that a lot of these reactors are going to be assembled more or less completely and potentially even fueled within factories, centralized locations, and then transported out to sites. So this creates a need to make sure those manufacturing facilities are secure. And it also means there's a need to reconsider the threat to nuclear transport operations, given these will increase in number, as well as potential attractiveness, given complete fueled reactor systems will be moving via road, rail, and sea and river. Could we have the next slide, please? Our next set of differences comes to do with operating capital costs. And because these reactors are much smaller, there is an absolute need to drive cost efficiencies through reduced operating budgets. So this means that we need to consider, for instance, how security headcount costs are approximately 10% in the UK, at least, of total power plant operating costs. And I've seen estimates that in other countries it can be much higher, as much as 25% in one example. So there's a need to replace this cost by inherent security by design in order to minimize those costs and make sure that the security is operating as most at the greatest efficient level of cost as possible. The other factor to consider is that many of these plants will have a reduced capital cost per unit. So it makes them available to a much wider range of states and operators than we've previously seen. And this means that we'll see rapid export potential, at least, going to a huge range of countries in the near future. But the question is, will those states be ready? Will they have the necessary organizational maturity in terms of independent regulators who can ensure that the standards of safety and security and so on are being respected? Could we have the next slide, please? Many developers are interested in moving as well as towards built-in inherent security, towards complete automation and remote operation of facilities. So we're going to be seeing a reduced role for humans in security and safeguards. Technology will take over increasingly roles in diagnostics, detection of threats, and delay as being applied to threats. And whilst this brings advantages, it also means that we're opening up greater attack surface potentially for cyber risks. So the cyber risk cannot be ignored. And what we're also going to see potentially is human decisions being increasingly supported by AI. And I personally believe that humans will remain part of critical decision pathways, but they'll take a much more supervisory, critical decision-making role rather than day-to-day monitoring. And on the other side of this, we'll see an increased movement of facility operation into centralized operating locations where numerous reactor units geographically dispersed can be operated from a single central location, with critical data crossing site boundaries into and out of nuclear facilities, which will need to be protected. The other side of this is that we're talking about response forces and armed response forces, for instance, being deployed remotely from the nuclear site. And so it will be vital to ensure that attackers can be delayed in their efforts long enough to allow those response forces to arrive. Could we have the next slide, please? So I won't go into the great detail of all of these many different reactor types and deployment scenarios and so on. However, looking across that full range of different reactor designs and fuels, we're seeing a few factors that are worthy of consideration. First of all, many of these developers are looking to implement passive safety by design features, and this can bring credit to security by reducing vulnerabilities and the potential consequences of sabotage. Novel fuel materials are being deployed and intended for use, such as high assay, low enriched uranium, plutonium fuels, various mixed oxides and other mixed alloy materials and so on. So it depends very much on the individual reactor technology as to how these fuel materials will affect it. But we need to consider some wider things, such as are the theft categorization tables, category 1, category 2, category 3 for nuclear materials, will they still be applicable in this world of new and weird and wonderful nuclear fuels? And in particular, there are challenges around non-fixed fuels. So 2 examples on the right of the trisosphere, which is about 60 millimeters in diameter, and then the molten salt fuel on the lower left, so the liquid fuel that flow, both these moving around inside the core during operation. And extended refueling intervals as well creates not only security, but also safeguards challenges. So we're going to be talking about reduced in-transit vulnerability and less fuel being stored at the site, leading to a reduced security demand. And I see someone is in the chat asking if we can get the presentation slides after the webinar. I would recommend that, at least for what I'm talking about now, that you have a look at the fuller report, which gives this and a lot more detail besides, and I'll provide a link to that in a couple of minutes. Could we have the next slide, please? So one of the key points about these small reactors is that they can be deployed and used in a much more wide range of configurations. So looking at, for instance, multi-unit sites where you deploy a large number of SMRs or AMRs onto a single site footprint, we're talking about things like aggregating of nuclear material between several reactors into a single facility. And as you can see in the image on the right, I'm kind of trying to get towards this idea of, if you have multiple units, each separated by its own high and low security areas, and there is no shared security facility equipment between them, then this creates the maximum security benefit, but it also means you gain no operational efficiencies by co-locating those facilities on a single site. Going down towards number 3, where all of the reactors share a single complete set of security elements, and this is kind of more, for instance, how things are done with New Scale Power, which is one of the more advanced developers in terms of how close it is to deployment. This is what they're doing. So they're sharing getting a lot of operational efficiencies by bringing these things together all in a single building, but perhaps some of those security advantages from separation are lost. Reduced footprint is something that many of these developers are wanting to go to, meaning that there will be potentially moving the boundary of the nuclear site very close to the actual nuclear facility, and therefore reducing the opportunity to import delay upon threat actors. And there's going to be therefore a need for earlier detection and more delay to compensate for that, and to assure that a response will be able to act within the time delay that we can provide. Remote and isolated nuclear facilities. Many of these designs are being talked about for deployment in places like northern Canada, Siberia, very, very isolated locations away from major infrastructure to support isolated communities, for instance. And when this is done, this creates challenges in terms of the costs and time required for staff to rotate back and forth between this isolated facility and their homes, and also the training costs and time involved in doing that. And it also increases response times, for instance, if you are not keeping your response force in that very isolated location, which would create a high cost. And finally, this is something I'm only going to touch on very briefly, but certain designs are designed to be transportable nuclear power plants. So a mobile platform on which the power plant is mounted and from which it operates continuously. So having your power plant be entirely mobile creates a range of security and safeguards and other considerations, which I won't go into great detail now. But for these ones, there are unique challenges, let's say. Could we have the next slide, please? So the final area of difference we identified was in developer business models and marketing approaches. Many of these developers these developers of these EID technologies range from large established nuclear developing companies all the way down to small startups of just a few people who have come together in order to start up a reactor design concept. And this creates challenges, particularly for those startup developers without large budgets, because it means they are incentivized to delay thinking about security and to pass that on to potentially even the operator to think about. And this risks making those designs effectively uneconomical to ever come into real life, because security hasn't been thought about and designed in. It's been left to the operator to figure out how to do it at a much higher cost. And when we have these small startup developers, the other risk is that they might allow for their technologies, because they're not used to necessarily protecting and applying export controls and securing knowledge, that technology could be passed to threat actors who might seek to integrate multiple sources of knowledge into something. And the final point I'll make is about reputational risk. So the point is that although all these developers are claiming that they are totally separate from this history of things like Chernobyl and Fukushima and so on, one incident with any EID will tarnish the reputation of all EIDs as a whole and the whole paradigm. And so it's key to not only detect and delay and respond to threats, but to deter them as much as possible. And new approaches to deterrence will be required in the absence of visible security. So if we could advance one more, please. So the report contains a number of recommendations, which I won't go through in great detail in the interest of time. But what we are saying, first of all, is that if you go and look through these recommendations, please do not think, for instance, I am a technology developer, therefore I will only look at the recommendations for technology developers, because one of my key points, and the key points from my colleagues, is that it's only through working together collectively that that we can realize the true benefits of EID, and failure to do so will only result in delays of these things being realized or potential failure. And there are recommendations here for research organizations, technology developers, and technology operators. And then if we can go to the next slide, we also provide recommendations for the regulators, national stakeholders, and the International Atomic Energy Agency. And as I say, I won't go through these now. Can we just go to the final slide, please? So you can find this report that I keep mentioning on our website. There's a short link there, and I'm sure we can put that into the chat for people to grab. In fact, I can do that right now. So there's a link in the chat there where you will find that report. And we also have a range of other publications on nuclear security culture and indeed nuclear security in general, which are available through our website, which is on the slide there at the bottom, kcl.ac.uk/CSSS, where you will also find more information about these webinars. So hopefully I'm not taking your job away there, Carl. But thank you very much for your attention. I will now pass the floor back to Carl.
Excellent, thanks, Ross. No, really, really well done. That's really clear and really interesting. So thank you so much. Great. What I'm going to do now is, ladies and gentlemen, thank you. That Mentimeter slide I put at the beginning. Apologies, there's a small issue there, but what I would like to do is just invite you to go to the details of the Mentimeter. So lots of links in the chats, and I'll put it in there again. But we have the code up at the top of the slide, if you can see it there. So 25784245, and I'll repost the link into the chat for everyone to see. But it's great to kind of just understand perhaps where people come from. I think a lot of academics in the room today. We have about 50 people in the audience. So I think we're a little way off. What I would suggest is please do put your affiliation, for want of a better word, in there. So, okay, so just Ross, you've been speaking to a lot of academics, but a good spread of people actually. So that's really good. I'm with the next speaker, Dr. Nielsen. I know this is pertinent to yours, so if I may, I'm going to close this question and move to the next. And this was the initial slide I had on, so some people have already answered this. If you've not already answered it, please do have a go now. How do you feel? So the question is, do you think society at large is ready to accept more nuclear technology or more nuclear power technologies? Interesting mix. So there's a very firm opinion that actually they will accept more nuclear power, but only after public debate. Very few people thinking that it's going to be an immediate affinity. Excellent. I will leave this up, but I think we're seeing more of a trend there. Okay. Also, we're up to 60 participants, which is fantastic. Excellent. Anita, I think at that point. Oh, apologies. I've put Christoph's slides next. So let me change up very, very quickly. So my apologies. But hopefully what I can do is leave up the slides there. So apologies, that appears to not have saved, but let me desperately put that in there for you now. So that should be coming up. So Anita, I'm so sorry, that wasn't particularly smooth. But let me say, can you see my screen now?
Coming, yes.
Wonderful. So Anita, apologies about that, but it's a pleasure to have you here today. If you perhaps just like to introduce yourself and your background before going into your slides, that'd be wonderful. But otherwise, over to you. Thank you.
Thank you very much. And thank you very much for inviting me to this webinar. My background is that I spent a lot of time with the Swedish regulator, early days, starting the career there, and then was recruited to the IAEA, where I started to work in the Department of Safeguards as the senior coordinator there with information analysis, and then was moved to safety and security with becoming the director of the Office of Nuclear Security and developed the security system at that place. And after leaving the agency, I have continued to work as an independent consultant. And the reason for that is that I find that the possibility of using advanced nuclear power technologies for the challenges that everybody stands in front of now is very important. It's important to solve the problems. It's important to prepare the ground and to understand precisely where to go and what to do. And of course, the nexus is the nuclear energy and acceptance of that, what is required from a climate perspective, and then the acceptability and the assurances that we can have for non-proliferation and security. If we then go on, the next slide, please. So just to mention that what I'm going to say comes from my own experience, but it also comes from a study that was made in the Global Nexus Initiative, which had a report comparing the technologies a couple of years ago. Next slide, please. I will try to point to the most important questions I think that we need to devote ourselves to in the near future. And starting off with that is the fact that these new technologies promise a lot. So they present themselves with solutions to the difficulties that have been the case with LWRs and LEU reactor technology. But we still don't really have proof that it's going to work. So the fact that we have new coolant system, we have passive safety features, the technology doesn't have always a dependence on external power, means that there is a possibility for remote operation. It can be deployed far away, etc. But is it possible and is it acceptable? Next slide, please. So if we select all the different technologies that we have as a possibility to some very principal difference and compare it with light water reactors, we can take molten salt, which has a melted fuel, which is a big difference. We can take the trisoline, which have pebbles, ceramic pebbles that have a very sophisticated design in themselves. And then we have the fast neutron spectre reactor, which is in a way more similar to the light water reactors because it has individual fuel assemblies. And it comes obviously so that the fuel is different in its chemical and physical form, but it also influences on how the data about the production in the reactor and what happens with the individual fuel assemblies, material in the fuel, also affects the way that we can track the information about the fuel. And you can see it over there. The refueling periods are also very important, and online refueling, as for molten salt and triso, of course, presents a particular problem from the safeguards point of view, because one of the very fundamental principles is continuity of knowledge. Another possible challenge is long operating periods in which the nothing happens, but still. So we can continue this with comparing what are the efforts required in the safeguard system. Next slide, please. So important for a wide deployment for next period of time is that the automatic association, when we talk about advanced nuclear technologies, an automatic association with weapons proliferation, that is decoupled somehow. And to say that somehow short is that I think it is important for the community to project a picture based on reality, of course, that this is a separate thing, that the possibilities are changed, and in fact, in a way, it can be a contribution to the non-proliferation system instead. Next slide, please. So in that regard, the IAEA verification of safeguards commitments, which are there as a result of the non-proliferation treaty, is essential. And in short words, this is a system which is composed of obligations by each individual state to declare all material, to be upfront with all the historic aspects of a nuclear program, to provide full information about what are the receipts and shipments, exports, imports, etc. Complete transparency. And the IAEA, on the other hand, has rights. It has the right to receive this information. It has the right to go out and perform inspections, complementary access, to apply basic and advanced technologies to learn that what has been reported actually also is correct and correct and peaceful purposes. And if not, the agency has the possibility, the power, one can say, to report the result to the IAEA board, which then can address any non-compliances to the UN and the Security Council. So this is a lot, actually. And therefore, for the future, I am definitely convinced that we should build on this. We should trust and implement the present system, develop it further, not change it. Next slide, please. So if we compare the features in the technologies with safeguards for light water reactors, you can see this table and you can study it later on. The point is here that the red dots are challenges, and the markups are basically a note of simplicity. This is possible to carry out in a uncomplicated manner. And what comes out of the picture is that there are challenges with techniques that are not single fuel assembly itemized based. So for the molten salt and for the TRISO, we do have a lot of challenges ahead. And then surprisingly, when it comes to the fast reactor and its design, it's only a relatively small challenge from the present perspective, namely the fact that fresh fuel can contain some amounts of plutonium. So this is something to think about, the whole picture, and it is also food for thought. If we move on to the next slide, please. What comes out of this is a statement that I would very much like to say, and that is that the IAEA can safeguard everything. And the only difference is that in some cases it may be easy to do, it may be cost effective, in other cases it can be very resource demanding. And since this new technology wants to be lean in costs and be easy to deploy, the designers should seek cooperation with each other, perhaps, but definitely with the IAEA, people that know about the system, to find a way of designing these powerful technologies so that it is also easy to maintain. Next slide, please. If we take a quick look at what are the security concerns for technologies at large, there are two items that comes up, and that is the possibility of theft of nuclear material, and in particular of the kind that can be used in weapons production or weapons usable. Or it can be a situation of dispersal of radioactivity that can come from an act of sabotage. Next slide, please. So if we then look at these features of the technology, we see immediately that, and I showed this slide also earlier, we see immediately that the technologies are important for consequences, for any resulting consequences of acts of sabotage. And the way to determine the seriousness of an act of sabotage and how to protect it against it is to have an understanding of whether the facility, the technology, can give rise to unacceptable radiological consequences. And this is something that designers, in my mind, should devote a lot of attention to. What are the consequences of an act of sabotage in different ways? And by analyzing that, it is also possible to see perhaps it is a good situation. Perhaps the radiological consequences, because of the technology features, are not so serious as compared with the worst cases of LWOs. And next slide, please. If one look at a table of comparing features of the technologies, we can see that all of these, which we have spoken about, in security terms and physical protection terms, are category 2 and 3 material, so not direct usable for weapons production, which means that there is, after all, a better situation when it comes to addressing the case of theft of material. One can also say from a security point of view that existence of passive safety features is positive, and the non-dependence of external power is positive. And then the last question is, what is the operating pressure? If there is an event, can the radioactivity become dispersed? And for example, how is that influenced by having on-the-ground or underground deployment? There are no answers here, but it is food for thought and items that definitely requires more examination. Next slide, please. So the challenges ahead, I would say, goes with starting to think about what is it really with the very small reactors? What remains as real challenges from a regulator point of view, for non-proliferation, for security, and of course for safety? So in addressing that, what is the source term build-up over time? How does this function with remote locations? And one of the very good features of small reactors would be the faraway deployment possibilities. But how much of an infrastructure support does it need? To connect to the present grid is one good thing. But apart from that, what are the police forces that can come? What are the rescue operations? And connect that to questions like what is needed. Challenges would also be that there is some kind of inertia in the system. We are used to now, we have many years of development, have a well-functioning system after all in place. Is it time? Is it ready? Is it possible to adapt that one to slightly or more difficult situations? Can we find ways of making more use of the safeguard system, getting to know the results that come out of it, the fact that the peaceful uses are verified, the fact that countries are transparent with their activities. And so the remaining question from my side is whether the policy community is ready to address the question of advanced reactors from these perspectives. And I think that was the last slide from my side, and hope for a good in-depth discussion. Thank you.
Excellent. Thank you, Anita. That was very comprehensive. Thank you so much. I think what I might do is go directly to our third panelist. Christoph, how are you today? Thank you for joining us.
Yeah, I'm fine. Thank you very much.
Wonderful to have you join us. I was going to say, if you just want to introduce yourselves very briefly, then over to you when you're ready. Thank you.
Thank you very much, and good morning, everyone. So my name is Christoph Horvath. I'm representing the IAEA. So in my background, I'm also a regulator as Anita. I worked 20 years for the Hungarian regulatory body, and I left it as the deputy chairman of the regulator. And then I started to work at the agency in a senior position responsible for the International Physical Protection Advisory Service. And currently I'm the head of the unit, which is responsible for the security of nuclear material and nuclear facilities. As you may see the title, that within the agency, we also started to use this NAR and also this EID abbreviations, but in our project concepts that was called small modular reactors, or SMRs, even if it includes micro and transportable reactors as well. Next slide, please. So in my presentation, you see that I like to say a few words about the key features, but only just to remain, because the previous panelist already told everything in this regard. Then I like to ask a question about the applicability, or your opinion about the applicability of the nuclear security series publications. Then a few words about the nuclear security challenges. I like to go a little bit more to the details, what we have heard earlier. And then I give you an overview of our activities, what we are doing in this regard. Next, please. So I really don't want to go into the details, but this is more like a summary of what was said earlier regarding the key features of these SMRs in general. So the safety, security, inherent design aspects, so it's less consequences, hopefully, from these facilities, and less frequency of any accidents or incidents. The core size is smaller, which have an effect on the consequences, of course. Also the lower pore density, so then it's any consequences either triggered by safety events or security events are lower. Inherent passive safety features, which means that the sabotage protection point of view, we have to consider that as a lower threat or the lower sabotage target, lower level sabotage target. The construction can be below surface, in ground, or even under sea level. So which means that either from the threat point of view, that there are different or new threat attack scenarios to handle. The modular construction approach, it was said that whether they are in one site or whether they are in one protected area or not. Increasing automatization and remote operations from the computer security point of view. And of course, that what is all coming from that, the size of the inventory and also the new design, that it has smaller consequences per module. So now in the next slides, I'd like to ask a question from you. So the question is that, in your opinion, are IENSS nuclear security series publications relevant to nuclear facilities applicable to SMRs? So the question comes that the SMR is a nuclear facility, but the NSS publications cover nuclear facilities in general and not going to the details regarding one type of facility. And the potential answers are those that, if in your opinion, fully So they are, this SMR is one nuclear facility, it's nothing more. Partially, so then what they say that there are certain features which requires some additional guidance or some additional considerations, or you see that you think that the nuclear security of SMR, so they are such different from the nuclear facilities that they require new guidance.
Thanks, Christoph. So everyone can see the results there. We have about 20 people who have filled it in. I'll just put the link in the chat again if you've not had it. But yeah, it would appear that most people think there's partial relevance.
Okay, thank you very much. So if we can move to the next slide. So then, as you see, just to refresh that what the nuclear security guidance consists of. So then we have on the top these fundamentals. Then under that we have recommendation level documents. We have 3 types, so 13, or 1 is for the nuclear material, nuclear facilities, 1 for the radioactive area, and 1 for those materials which are out of regulatory control. So from our point of view, this IAEA nuclear security series number 13, which is on the left bottom document, this provides recommended requirements, so what to do in order to protect nuclear facilities and nuclear materials. And speaking about the how, so we have implementing guides and technical guidance documents. The most important implementing guide, which is a vertically covering all nuclear security areas, so all measures from deterrence, detection, delay, response, and also all the security measures like trustworthiness verifications, insider prevention, protection, sabotage target identification, all sustaining the system. So all those topics are discussed in a overarching manner in this number 27G. But of course that there are many additional implementing guides and technical guides which are covering one topic of the nuclear security series. There are over 40 such publications, and I don't have a link here, but if you Google it, all of them are free of charge downloadable from the IAEA website. Next slide, please. And here in the next slide, I like to speak about the nuclear security challenges, what we have identified. So we have we already started this project like 2018. So when we already recognized the need for such time or the coming nature of this revolutionary new design reactors of these SMRs, and then we started to make an assessment whether our documentation is applicable to the SMRs or not. So it relates back to the questions what you have. So then we had a consultancy meeting with experts from those states in that time who were most relevant or most concerned by the SMRs as regulator, vendor, potential regulator, potential operator. And that time it was said that in general, those what is written in the implementing guides and also in the recommended requirements, they are applicable to SMRs. But the CM or these consultants also highlighted or draw the attention of the agency that as more information will be available, then we should reassess this applicability. So we already have a program for these consultants because we would like to provide a document. Currently, we are thinking in a tech doc level, which is a document which is can include case studies and can include implementing information from the member states, but not include guidance for the member states. So, and in this, during the development of these documents, we already identified certain challenges from security point of view. So this underground construction, so then it's very clear that the attack scenarios can be different. So if it's under the ground, then maybe a vehicle with explosive on the top of this area where on top of the site can be an attack scenario. Also, it's an interesting how the off-site response forces can have access to the facility, including also other services like firefighters, how they have access to the facility if something happens inside. Also from the evacuation point of view, how it can be organized by the security staff as needed. Sharing threat information is a big issue, as we say, because typically the threat information is a national responsibility. It is used by national intelligence, and information from them to share it with vendors or with other states it can be an issue, and it should require certain guidance how to do this, or some information. The use of advanced fuel, it was already said that it is important from the categorization point of view. We typically consider the quantity, the irradiation, and the enrichment of the material, and of course the type, whether it's uranium, plutonium, or thorium. But we should consider also whether this chemical and physical form, as it was already discussed, whether it has an effect from unauthorized removal point of view, and of course that whether it has an effect from the sabotage point of view and the radiological consequences point of view, because as you know that above the high radiological consequences, we need to have vital areas and also sometimes inner areas for such materials. The remote deployment is more from the offsite response point of view, so it needs time to have a offsite response force if some attack occurs in the facility, and also it relates to this computer cyber security which is mentioned here. So then it requires more and more computer security related issues. The compact design has an effect on the consequences. One more issue I like to highlight is this transport security concern. So far our guidance covers when nuclear material is in transport in a container. But in this case, the entire facility with its safety systems are transported. So we should also consider, so whether from sabotage point of view, during the transport, not only the material is a sabotage target, but maybe also the safety systems as in a normal operating facility or land-based facility. Next slide, please. And regarding what we are doing, so now we are developing a tech doc on the security of these SMRs, and it should be finished by the end of this year, and hopefully it will be published next year. We also were initiating coordinated research projects. These are the CRPs, one for the computer security related issues and one for the more physical security related issues. We hopefully would like to include vendors, designers, regulators, and operators as well. From security point of view, we have many joint activities with safety and safeguards regarding typically the interface with safety and the interface with safeguards. There is also a document we are working, or we are contributing this application of safety standards. It also covers the interface with security and the interface between safeguards and security. And another tech doc are under development on the security, safety, and safeguards by design for SMRs. There will be a technical meeting in the beginning of June. So this document is hopefully published also in the next year. And we also have, for computer security, we are also working, and we have certain meetings on that. Thank you very much. So as a conclusion, so then IAEA is coordinating with member states using the information from the member states for the security. So that's why we have this pool of experts, and we are using them as consultants for us and helping us. One effort is to really review and synthesize how these SMR specific features have an effect on the application of our requirements and also our guidance. We would like to initiate coordinated research projects to involve more and more people who are concerned or interested for these SMRs, develop a new technical document, and also working for a one-house approach together with safety and safeguards. And that's concluded my presentation. Thank you for your attention.
Wonderful. Thank you so much, Christoph. That was really fascinating. And thank you to all of our panelists for their presentations. We have about 7 minutes now, I think, for the next part of the webinar, which is just questions and answers. So I see a couple of raised hands. Apologies, the webinar format in Zoom doesn't really allow conversation. So what I would ask politely that if you could put your questions into the Q&A box, we'll be able to keep an eye on them there. And I can see a couple of questions which have come in. So please do use the Q&A box. I'm sorry we can't really ask people to unmute themselves. My apologies there. But one thing I might do just while we are waiting for some questions, I have a couple of my own, and what I will do is perhaps go back to the Mentimeter slide, which everyone so diligently filled out, so thank you. Anita, I think this was actually originally based on one of your questions you wanted here, but about whether society at large is ready to accept more nuclear power technologies or certain types of technologies or under conditions. Can I ask, Anita, first of all, are you there? But second of all, do these results surprise you? Do you think that is accept the right way? Should we be thinking about the way in which society accepts this new potential, this promise? Is there a way which we can make it perhaps more mainstream, or does it deserve to be an outlier in terms of public perception?
Oh, this is a very good outcome of the question for the Mentimeter. I'm glad to see that there is much more confidence in the system than I thought originally, and I think there are two kinds of answers to that question. One is that everything is not known about these technologies yet. So there is a lot more to learn about what actually happens in reality, and what is it that today we do not know of that can turn up as consequences later on. And normally in the policy community, politicians and leaders in big organizations, etc., they are aware of that promises are promises, but they need to be proven. And in particular in the area with radioactivity. So we are here speaking about nuclear energy, nuclear power, but it is associated with radioactivity and the possibilities of accident and the possibilities of security events. And these people are not, it's not easy for many to speak in positive terms about it. And we can see signs of that, I believe, for example, in the discussion of the European Union now, where to go with the energy questions, and how the nuclear energy part is having had to struggle to come in as a mentioning of clean technology in the final documents, which I think that everyone who has said yes over there, and myself and others, would think it's a no-brainer to do that, but it hasn't been, and it is still a struggle. And that is why I raised this question, because I think more attention needs to be put to that, to make it comfortable for policy leaders to speak in positive terms about the technologies, of course, providing that they have proven their features.
Thank you, Anita. I'd just like to invite the other panelists, Christoph or Ross, if you have any other comments perhaps on this, or response to the need for public acceptance for this new and novel type of technology. Perhaps Christoph, did you have any thoughts?
I fully agree with Anita, and also I agree with the answer. So I also answer the same way. So I think that this transparency is such an important issue. Of course, that in the field of security is more tricky how to manage this, how to make the public confident that we are providing sufficient security for these facilities. But I agree that if the public supports that, either from culture point of view, either from deterrence point of view, or even from detection point of view, that's a very huge step and a very important aspect of deploying nuclear facilities. Thanks.
Thanks, Christoph. Ross, any thoughts?
Sorry, Carl, I'm having some technical difficulties with hearing the questions. Could you repeat, please?
Oh, no worries. It was on the importance and need for public acceptance with the particularly, I guess, the new novel reactor, one thing you emphasized in your presentation was the reputational aspect, that one catastrophe or one even accident or similar could taint the image of this new technology type. It's already controversial through historical reasons, Chernobyl, Fukushima. But I guess my question is, have you seen any movements or developments in the understanding around public acceptance of this new technology in particular?
So I have looked in the literature for examples of public acceptance as applied to SMR and so on. I haven't found anything specific on this. The only thing I found was something that indicated that the public are capable of making decisions about their choices in nuclear energy. So when offered a kind of, do you prefer this type of energy or this type of nuclear energy or this type of nuclear energy and so on, people were capable of understanding and articulating a preference, which I think is an important thing to bear in mind as we kind of go into these debates. We shouldn't kind of try and maintain this as a technocratic discussion between experts. But to the other point about public acceptability, yes, this is something I'm very concerned about, is we have a number of developers, some of whom are making claims which I would suggest are unwise. For instance, putting out marketing material that says nothing can ever go wrong with my reactor. It's absolutely impossible that there could be any problems. It's the safest thing in the world, and there will never ever be an issue, full stop, the end. And I would suggest that actually every time there's been a nuclear disaster, it was as a result of scenarios that were unforeseen and things that people didn't think would happen. So to kind of make these claims that nothing can ever go wrong is a foolish thing to do, and undermines the kind of seriousness and sobriety that's needed for discussions around nuclear energy.
Thanks, Ross. I see Anita's put her hand up. Anita.
Yes, I just wanted to add that I think that there are two communities here we need to address. One is the public acceptance, and I share your view there, Ross, that the trend in the public acceptance is going up, and we can see it in my own country, but I think in more places like that. But the other community is the policymakers, the politicians, who has had to struggle with the questions of doomsday scenarios with nuclear accidents and the connection to nuclear weapons and all of that. And they are, probably for good reasons, very cautious about what they are saying. But I think for the projections to come through, there needs to be it needs to be for them easier to answer questions. So some attention also to that community was what I was asking for, to make it easier for them to address the questions.
Thank you, Anita. I know we're over time now, so thank you all for your patience. One thing I would like to try and get one or two questions in from the chat. Perhaps this one leads in most directly from your point, Anita. But a question from George. You mentioned that the policy community may not be ready for advanced reactors. Can you elaborate on the nature of that unpreparedness and the reasons for that? So just building actually on what you said just now.
Was that a question to me or to George?
Well, from George to you, Anita.
Yeah, okay, all right. I think I elaborated a little bit on it already, that let me put it from this view angle then, that this should be very important for designers to deliver hands-on information and test results or whatever it is, to make it easier to answer the questions. It is obvious from the list of features of the new technologies that there are possibilities over there. and I know that it has also resulted in more favorable views from a lot of people in the general public. But I do believe that a little more is needed for the policy community. More actual information about the design. I can give you an example. I have asked several times, what is the core content of a very small reactor? Very small reactor. And no answer yet. Maybe it is over there, but you know, these questions that come with the smallness are of a different nature than the question that comes with having large facilities. So not to transfer the questions and answers from the big facilities into the small facilities, that is a tricky transfer.
Thank you, Anita. I know we are over time, as I say, but there's a question that's just come in, and perhaps for Christoph. Just a question here, perhaps related to the guidance you mentioned or referred to in your talk. It's a question from Anonymous, but just about the IAEA guidance and the tech docs. Is the agency looking at developing guidance for SMRs at the moment?
So, as I told you that currently we think that we have guidance, implementing guides and technical guidance, which are consensus documents of the member states. So it means that going through all the member states and accept it as guidance, we don't plan such, because we think that what we still have, it includes all those information what is needed. What we think that as a first step, we would like to provide some implementation information, that how it is implemented in certain member states, how we can also publish the result of this assessment, how it is implemented in member states, and what considerations or challenges are identified by those experts who are working with us. And we can easily publish this as a tech doc. If we publish it as a guidance, then it requires much more time and much more consolidation. But in this case, we have a chance to publish it as soon as possible. And later, of course, that if we feel a need or if the request will come from member states, then we will work on a guidance as well. Thank you.
Thank you for explaining that. That was very well put. I guess my last question for the panel, so thank you all for your time, and apologies if I haven't got around to answering your question. A question from Mr. Jeffrey Allen. Cyber risks have been mentioned in today's presentations. Can the panelists elaborate further on how one strikes a balance between the use of remote monitoring and operating systems for SMRs and guarding effectively against unauthorized access via potential cyber pathways? I hope that's clear, but how do we balance, particularly as if we're looking to minimize costs and increase automation, cyber obviously becomes more important. Do the panel have an opinion on how we strike that balance between what we're used to in terms of physical and human, or a brave new world of artificial information and the like? Do you have any volunteers?
Yeah. Let me start off in that case. I think that the question is right on spot. And I believe, and we had a discussion last week about this, and it becomes clear that almost everything in the new facilities are digital. And not enough is known about how that can interact by itself, but also with other systems. So the digital systems offer great solutions and great opportunities, but they need probably much more in-depth analysis and thought power about how to prevent attacks, how to prevent coming in with different codes into the system that could be detrimental, and then also to couple that with what are the consequences if something should happen. So it's not only to deal with the IT technologies, I believe, but one has also to look at what would happen in reality if something is injected into the IT. So good opportunities, but more in-depth analysis.
Thank you, Anita. Yes, building it in, not building it on, I'm sure. Christoph, Ross, did you have any comments on that? I think, Ross, you unmuted first, if I may. Ross.
Yeah, I'll briefly say, in terms of striking a balance between the use of remote systems and guarding against cyber threats, I don't think it's, I don't know how much of a balance we can realistically strike, because I don't think we're going to be able to necessarily, nor would we want to, from a security perspective, prevent the use of those remote systems. And I don't think we're going to be able to realistically say, I'm sorry, remote operation is too risky from a security perspective, it's not going to happen. Realistically, I think as security professionals, it's going to be a requirement that we find a way to make this work. So that would be my key point, I guess.
Thank you, Ross. Christoph, last comments.
Yes, I just like to echo that this area is also one in the limelight of the agency as well. So computer security experts are also working on a document and checking whether the existing guidance is sufficient or additional guidance is needed. And just for the last verse, that I would like to encourage all experts. So if they are interested to be involved to IAE activities, then we are open to involve more experts who can provide information which is useful for all other member states. Thanks.
Thank you, Christoph. And that's a wonderful note of cooperation to end on. So I think I will use the opportunity to draw this to a close. Thank you to the panel for joining us today. It's been a pleasure to work and speak with you all. So thank you so much.
Thank you.
Wonderful time. And thank you again to the audience for your time and your patience. I know it's beyond the hour and many of you are busy, so thank you so much. What I would like to do is, before we go, is to thank the panelists again, but then to invite you as well to our next month's webinar. We'll have another panel, and we're going to be looking at gender diversity and increasing inclusion in nuclear security. So thank you all for your time, and I look forward to seeing you next month for the next webinar. In the meantime, thank you again for joining us. Lastly, if you have enjoyed the webinar, or even if you haven't, please don't forget there will be a survey which will be prompted when you close the Zoom. So please do take the time to fill that out. It's really useful for us, so please don't forget, that's an important part of the webinar as well. So thank you all. Anita, it's been a pleasure. Christoph has logged off, but Ross, thank you so much for your help, and for Sally, who's in the background as well. Excellent. Thank you all. Have a wonderful day. Bye.
Bye-bye.
Thank you all. Goodbye.